now that Frank has had a chance to speak, I'm in a better position to finish off a few points that I began to make this morning. So what we're looking at is we're looking at these kind of ordered structures. So we had a certain class of, so we had these ordered structures that I was looking at, or orderings, ordered structures. I was looking at here and comparing them to proof theory. So we're looking over here, and I want to just flesh this out a little bit for you so that you can see what's going on. And what we set up was the idea that we have, which means we have a less than or equal to, which is reflexive and transitive. I'll just write RT there. Okay, and here we have an entailment relation, okay, that we're dealing with there. And so what we said is, we have something, a greatest element, which we call top, which is A less than or equal to top, which on the proof theoretic side, if you just look at it in terms of true, would be that regardless of whenever A is true, nevertheless top is true in every single case, which is, so it's the trivially true proposition. So we had that. Then we spoke of having meets, so we had this semi-lattice structure. So we have this part is a repeat of this morning, okay? And we wrote this, so we wrote that over here as A and B true entails A true, and A and B true entails B true. So we had that, and then we said it was the greatest lower bound. So we have this, that's as before. That should be B. So then C is less than or equal to A wedge B. So that's the rule. This is so these corresponded to what Frank called the elimination rules. And then the introduction rule is if A true gives us, let's see, B true, let's do this so it lines up. Okay. C true gives us A true, and C true gives us B true. Then C true gives us A and B true. So that's what we said this morning. Then if you add in the additional stuff that Frank did with you, then we also have so we can think of these as just axioms. I'll write a line over them. They're rules with no premises. So then we have the dualization of that. So we have a least element. We have that everything is less than A, but the bottom is less than A. And that's just the idea that if false is true, then anything is true for any A. So that's the elimination form. And then we have the idea that the idea of join. So this is the nullary join. So we have that A is less than or equal to A or B. And we have that B is less than or equal to A or B, or A join B. Because if you think of this as the least upper bound, it's above all an upper bound. So being an upper bound, it means that A true entails A or B true, and B true entails A or B true. So you've got that so far. And then it's the least of all the upper bounds, right? So that says if A is less than or equal to C, and B is less than or equal to C, so if C is an upper bound for A and B, then C has to be at least as big as the join. A or B is less than or equal to C. And as you saw in Frank's lecture, I'll just write it over here, that corresponds to the idea if A true entails C true, and if B true entails C true, then A or B true entails C true. So that's the same, this is the exact same structure, okay, that we have there. And now I didn't quite leave myself enough room. Okay, so that takes care of, so at this point, we have the structure of a lattice. Okay, that's the terminology. So it's a preorder with all finite meets and joins. Okay, so that's just by definition, that's called a lattice. A lot of times, especially in computer science, people throw around the word lattice and think that it can mean anything that they feel like it meaning. Like they'll refer to the subtyping lattice in, Java or something, and it's not a lattice. You don't have joins. Okay, so it's better if we stick to established and meaningful terminology. So this is what is meant by a lattice. So this is a lattice structure. And then, in addition, Frank had some rules for implication. And the way I want to do that, there's different ways we can do it. Let me just find what I wrote down here. Give me a second while I find my way. Right. I'll get to that in a minute. Okay. Dun, dun. Where did it go? Oh, there it is. Right. Okay, so one version of it, there are different versions of it. I wanted to write it down clearly. So, which corresponds to the following idea. So one is that one way to write this down is to say, if we know A is true, and we also know that A implies B is true, then we know that B is true. That's an axiom. And another axiom is, another rule that comes up here that says, if C true together with A true gives us that B is true, then with the ambient C true, we know that A implies B is true. So this was the implication introduction, and in one form or another, this is the implication elimination. There's there are slight different ways to formulate it. So for example, you could take this as a premise of the rule and then use the entailment. I mean, there are different formulations of it, but it all sort of amounts to the same thing, okay? And from an order theoretic point of view, what that's saying is you can phrase this in one of two ways. One is to say, A meet B is less than or equal to C if and only if A is less than or equal to either B implies C, or another way that this gets written is C to the B. Written C to the B. Okay? That's the structure. And that's uniquely characterizes this implication connective. That determines it up to isomorphism, and in this case, up to its order identity, being the induced equivalence relation of the preorder. Another way to sort of see this, so that's one way to say it. But if you take, for example, what we can get out of this is if we take, what do I want to say? Give me a moment. Well, anyway, yeah, I think that's the main thing I want to say. And I could also write this down in the following form. That says, if I take A meet A implies B, excuse me, or B to the A, then that's less than or equal to B. That's one way to order it. And if C meet A is less than or equal to B, then C is less than or equal to A implies B, or B to the A. Okay, that's an equivalently. We could either take this definition, okay, one, and when Steve talks, he will explain all the ins and the outs of this too, and we do that. Okay, so in other words, the implication corresponds to an additional closure condition. So we have meets and joins, and we also have what's called an exponential. Okay, so this is the exponential object, C to the B. And such a structure here, which we have going on here, I'll just draw a line. This structure is, my board discipline isn't the greatest. This forms the structure of what's called a High-Ting algebra. That's the definition. And what we're going to do is so the point being that the proof theoretic concepts which are written here, which is this is intuitionistic propositional logic that is written out with and or true, false, and implication. Intuitionistic propositional logic corresponds algebraically to the concept of a High-Ting algebra. So that's the sort of first thing. So this is the sort of algebraic structure. And the High-Ting algebra is an instance of this is called a Cartesian closed preorder. Okay, and Steve will tell you a lot about that. This is a particular case of a category as a preorder, as I mentioned to you before. And being Cartesian means it has a product, which is a Cartesian product that satisfies these conditions here that I mentioned before and drew diagrammatically. And being closed means that it has a exponential that satisfies this condition. And it's an exponential, so it's closed with respect to the Cartesian structure. And so that whole thing is called a Cartesian closed preorder. Okay? So that's the idea. Okay, so generally, in this context, closed means that the maps, the less than or equal to relation, which is the maps between A and B, A less than or equal to B, it can be thought of as the maps from A to B, are internalized as elements of a particular type or an object in the category, which is the exponential object. And that's called a closed structure. And there are situations, I don't remember whether anyone's lecturing on substructural logic this time, but if they were to, then you would run into things called monoidal closed structures, and you would run into other forms of closed structures. I'm not sure if that'll come up in this instance of the summer school. Okay, so that's the notion of a Heyting algebra. And the notion of a Heyting algebra is extremely closely related to the notion of a Boolean algebra. Okay? The only difference is, let's look here, is whether you have a complement. So remember, so what we notice here, if you look at, let me just kind of catch my notes here for a second. Are you with me so far? Oh yeah, I want to say something about, remind me to say something about structural properties. Okay, so here's the idea of a complement. So we define, so Frank defined, I think he wrote it like this, not A by definition to be A implies false. Okay, or sometimes a notation that people use is A bar maybe. Okay, in certain situations, people like that notation, so you can write one or the other. And this has the feature, okay, that we know that if we take A and A bar, if you look at it algebraically, it's less than or equal to false, less than or equal to bottom. Since bottom is less than or equal to everything, you can really just say it's equal to bottom. Okay? This is a trivial instance of this rule. If you take this principle here, and you make it be A implies false, then you're less than or equal to false. False is less than or equal to everything. So the two together will give you an equation, or the induced equivalence, that is, the equivalence, the induced equivalence of the preorder. But let's just write it like this. So the idea is that this has some of the flavor of negation. Okay, this is called negation. Okay, and in fact, that's the way this is defined. And the other thing you'll notice is that is the following kind of intro principle. This is kind of the elim rule that says if C together with A is less than or equal to bottom, if that's contradictory, then C is less than or equal to A bar or not A, depending on how you look at it. Okay? So this is sort of the introduction rule for negation, and this is kind of the elimination rule for negation. Okay? Now, the thing I want you to see, the thing I want to bring out here, okay, let me catch to this. The reason I want to bring this out, okay, is that, okay, so you're with me so far? Okay, so that's a notion of negation. So any Heyting algebra comes equipped with a notion of negation satisfying these principles by virtue of this definition, okay, because you have an exponential. So that's what I'm saying here. However, there's something to say about this that is worth bringing out because it is of the essence of intuitionistic logic, which we do not, so from an algebraic point of view, is the negation so defined, the internal negation in a Heyting algebra is not a complement in general. That is, what this means is we do not have, well, the best way to say it is it is not the case that top is less than or equal to A or not A. That's the way to say it, okay, in terms of the preorder, okay? In terms of logic, it says we do not expect to be able to prove A or, well, if we write it in logical notation, A or not A is true on the basis of no hypotheses. That's what is going on here, on the basis of no hypotheses. That top being here, assuming, if you think about it as an assumption, you're assuming nothing, or in terms of the order theoretic structure, something is absolutely true means the top is less than or equal to it. Okay, that's the definition. Everything's less than or equal to top. So if top is less than or equal to it, it's true. It's absolutely true. It's not the case that for every single A or not A or its complement, or A or not A, comes out to be true. If that were the case, you would have what is called a Boolean algebra. Okay? So a Boolean algebra is a Heyting algebra with a complementary negation. That is, where the negation behaves as a complement. We have this condition. Okay? But that's a very special case. And why is it a very special case? Because, and now this is a nice opportunity for me to make a point about the nature of constructive logic, which, from the show of hands this morning, I have a suspicion that some of you either already know or have intuited, but anyway, let me articulate it for you, okay, because I think it's worth doing it, which is the following idea. It seems superficially that since I don't expect A or not A to be true in general in this intuitionistic setting, it seems as though that's a loss, right? It seems as though something is missing that you're expecting to be true. And so you feel like that's bad because it's a loss. I say, on the contrary, and this was the point that Brouwer made in the 1930s, and no one understood him then, and it's taken a long time for people to understand what he was talking about, which is to say that no, this is not a loss at all. What it is a pure gain. Okay, it is a pure gain. Why? Because we can say, look, a proposition, by definition, we'll say a proposition is decidable if and only if either it or its negation is true. So all that's happening with intuitionistic logic is we're not saying, what we're saying is not every proposition is decidable. And if you take this principle, because it's not always the case that A or not A is true, if you think about that for a minute, if you think about what I was telling you right from the beginning, that we're doing logic as if people matter, what this means is, right, if the fact that there are undecidable propositions is the simple observation that there are unsolved problems. There are problems for which we neither have a proof nor a refutation. A refutation is a function, by this definition, that transforms any proof you think you have into a proof of falsehood. So we'll call that a refutation. So what we're saying is that a proposition is decidable if it has either a proof or a refutation. So if you look at, for example, equality over the natural numbers. So if we have x, y, and n, and now I'm starting to get toward dependent types, but I'll just do it loosely here at the moment. Excuse me, this is a proposition. Okay, so this is a proposition. It's a two-place proposition, and it's supposed to be equality. I claim that this proposition is decidable. That is the idea. Given two numbers, it's clear whether one is equal to the other or not. Okay? If, on the other hand, it were over the reals, then you also could have a proposition. So let's write sub n here just to make it explicit that so we don't get confused by the notation. If we have equality here as another proposition, I claim that this should be decidable. This is not decidable. I can give a proof of that, which I'm not going to do here at the board. But the intuition is, right, you can code up the convergence, for example, of a Turing machine computation as the decimal expansion of a number or as a Cauchy sequence of rationals. And according to whether it somewhere along the way moves away from 0 or not, it's according to whether the machine halts or not. Okay? So there's going to be no way to make this decision. That's just a way of saying it, like a heuristic guide to what a proof would be. Okay, so the point is that, or here's another one, is the famous P is equal to NP conjecture, which expresses a perfectly good proposition, and it's not known whether that is true or false. Okay? So it is very important to understand this point because, you see, the assumption that negation is complementary is the brute assumption that everything is decidable. Every proposition is decidable. Everything is either true or false. So this is what leads to people to characterize conventional logic done with, like, on the basis of a Boolean algebra as kind of omniscient, because it's logic as if people don't matter. The metaphor being, God knows which way it is, so every proposition is either true or false. It's just a matter of whether we know it or not. So from our point of view, as finite beings, from our point of view, it is simply not the case that every proposition is decidable. Now, there's an interesting consequence. There's an interesting subtlety here, which I would like to draw out to make sure you understand, which is the idea that failing to affirm the decidability of every proposition is not the same at all as refuting the decidability of every proposition. Okay? Be on your toes. Okay? Did you understand what I said? Okay? The fact that not every proposition is decidable is not the same thing as saying that every proposition is undecidable. That's a different thing. And as a matter of fact, it's a theorem, and I'll give this to you as an exercise. It's a theorem of intuitionistic logic that it is not the case that, in general, for every A, this is for a generic A, okay, not A or not A. In other words, you have to watch how you read this, because I don't want you to think this is just like some arbitrary game. This is a meaningful statement. It says, intuitionistic logic does not refute the law of excluded middle. Okay? That's what's important. It doesn't affirm it, but it positively does not refute it. It is known not to refute it. So what is so interesting about this? So the proof is an exercise. This is a very interesting exercise. You have everything you need to find this proof. That is, everything that Frank has told you is sufficient to solve this exercise. But I suspect you'll find it a little tricky. It's not that straightforward, okay? In fact, when you do find it, you'll be uncertain whether you're cheating or not, okay, until you go through it a few times. Okay, so I'll leave it as an exercise. But why is this important? It's important because, what is the importance of this? The importance is we can always heuristically assume that a proposition is decidable, even if we don't have a proof that it is. Because, you see, intuitionistic logic is not going to refute the decidability. Okay, that's the idea. It doesn't. If it refuted the decidability of arbitrary proposition, then if you threw in the assumption that it was decidable, then automatically you're in a state of sin, and so everything is inconsistent, and it's a mess. But here what we can do is we can make assumptions. We can say, well, suppose we consider that equality on the real numbers, let's say inequality on the real numbers is decidable. Then we can describe, for example, Newton's method for finding roots of a function by a kind of binary search procedure that requires knowing, okay, where are we relative to the x-axis, let us say. You can't actually do that. That's bogus, okay? It's not true. Okay, but intuitionistic logic doesn't refute it. So I can throw in that assumption and then act as though it were true. So in other words, the apparent limitations, so this is something that poor Brouwer, could never get across to anyone. The apparent limitations of IL, intuitionistic logic, are the very source of its strength. And its strength and its expressive power. Its strength and expressiveness. You see, it's just pure loss if you impose the blanket assumption that everything is decidable. Because you now are unable to draw the distinction between scenarios in which things are decidable and which they're not. Everything has been forced on you, okay, so you can't draw the distinction. Whereas with intuitionistic logic, I can selectively introduce decidability assumptions according to my preference in a particular situation. Maybe I wish to discuss Newton's method, and it's a nice algorithm, but for the fact that you can't compare real numbers for inequality. Okay, so it's a sensible thing to entertain. Whereas if you insist on that holding as a matter of pure logic, then you're out of the game. You can't even play this game. There are many implications of this point, and in fact, when we get to the end, some combination of me and Steve and others will talk about recent advances in type theory that I alluded to earlier that are entirely possible exactly for this reason. Okay? The only reason it works, the reason it's such a beautiful way to go is exactly because of this and related concepts, this idea. Okay, so I think that's a really critical idea to get across. So it's a good thing, okay, to be working with a Heiting algebra and not a Boolean algebra. So what this is saying is that it's one of these things that has the flavor of, puts me in an awkward position as a teacher. It has a flavor of, I have to say to you, in all honesty, everything you know is wrong. Okay? You have to start over. So everybody told you all this story about Boolean algebras. Just forget it, okay? It was a mistake, okay? They led you down the wrong, they're good-meaning people, but they led you down the wrong path, okay? So there's a certain amount of undo that has to happen in order to understand the real theory of programming languages and how it all works. And this is one of them, is getting used to this like core idea. Once you get the idea and start playing around with it, as I say, before very long you'll think, oh my God, these other people are crazy, and that's true, they are, and you'll figure that out. Okay, so that's like a little bit. I wanted to wrap up a little bit that algebraic story because I wanted to bring in the notion of Boolean algebra and compare it to the notion of Heiting algebra. And in order to do that, we needed to develop a bit more of logic so we can see how it works. So now, if you look at it, by the way, if you now go to a conventional textbook that you can download from Amazon, I think you'll be able to put things like the completeness proof for propositional logic will look a lot clearer and cleaner to you than maybe they have before. Okay? Yes?
Are you saying that we should forget about that intuitionistic logic is much better?
Well, classical logic is a special case of intuitionistic logic.
Yeah. But do we know if, how can we know if intuitionistic logic is primitive enough?
We don't.
Okay.
So this goes on in many other such variations. But what I want to be calling attention to here is this was historically was the first move, and in certain technical senses is a very important spot. But it's not to say it's the only move you could make. Okay, so and now that brings me to a second point. Okay, so I'll say it now in order to wrap this up. Okay, so I will answer your question in this way. So the thing I wanted to get across too is I just wanted to relate like textbook treatments of logic to this proof theoretic treatment by bringing out the order structure. A lot of the textbook treatments are not so good, in my opinion, at explaining this idea very well because they don't connect the less than to the idea of entailment. And they don't have at their disposal typically the machinery of natural deduction, which is what Frank was explaining to you before, which makes the whole thing seem natural and inevitable. That's just a personal opinion about why I feel it's so awkward in the usual treatments. But anyway, now you can see pretty clearly what that correspondence is all about and why that's there. I wanted to say one other thing about the properties of entailment. So if you look at, there's one thing I was a little bit fudging earlier, I did that deliberately, was the idea that the entailment has multiple hypotheses. So if you look at this from an algebraic point of view, what is the less than that is in question here? Well, what it is it's the meat of all of these things. Okay? So what you do is we can just relate this to that. Okay, that's the idea. We can think of that as the meat. The reason I bring it up is I want to talk about what are called the structural properties of entailment. And this is, in fact, an answer to the question that was just asked. Okay? So the structural properties we talked about so far, I won't repeat, are reflexivity and transitivity. But in general, we have an additional one. And one of them is called weakening, W, which is usually written like this. If you don't mind, I'll start using the conventional notation, write that gamma. Okay? So what we do is usually say, well, if A is true on the basis of gamma, then surely A is true on the basis of gamma and some other random lemma that has nothing to do with anything. Okay, that's called the principle of weakening. Okay, so that's the idea. So in terms of a preorder, let's look at what's going on. That's saying if gamma is less than or equal to A, then gamma and B is less than or equal to A. Well, for sure, because Is that what I want to say? Yes. If gamma is less than or equal, the reason is that gamma itself is, no, where did I go here? I had the thing in my head. I wanted to show that this is obviously the case. So the idea is that, oh yes, right. So gamma and B is it's a meet. So it's less than or equal to gamma in particular. And that, by assumption, is less than or equal to A. So what the hell did that, oh. So the reason I got confused is because I wrote the wrong letter. I'm thinking, how am I going to do this? Okay, excuse me. Okay, you try this and stand up here and you'll see. Okay? Okay, yeah, so I screwed that up as usual. Okay, so this is less than gamma, which is less than or equal to A by hypothesis, so you'll get the thing below the line. So it's a property of the meet that makes that come out to be true. There are other rules which are called contraction and exchange. And contraction, you might have seen this before, that says, this is an interesting one, that says, let me write it down and then I can explain it to you. It almost looks a little weird. If I can get B on the basis of 2 copies of the same lemma, then I can get B on the basis of 1 copy of that lemma. Okay, that's what that is saying. That's why it's called contraction. So you can almost say it's in the presence of this rule, there's no distinction between the top and the bottom. But in a certain way, you can say, if I appealed to the proof to a particular lemma A twice, then you can sort of appeal to it once and use the result twice. You know, that's essentially what it's saying. So from an order theoretic point of view, this is simply saying if you have gamma and A, and if that's less than or equal to B, then surely gamma and A is less than or equal to B. Well, why? For the same reason I gave before. So this thing is less than that thing, which is less than or equal to B, which is therefore less than or equal to B by transitivity. So that's an easy one. And then there's also exchange. And exchange says, and we'll write it like this to be like as general as I can think of doing, which is to say that the order of the hypotheses doesn't matter. You can do any permutation can be written as a composition of swaps, right? So I just have to work with the 2 swaps. And so from an order theoretic point of view, you can write it out again. You can say, well, this and A and B and delta. If this is less than or equal to C, then this and this and this and, whoops, and delta is less than or equal to C. And the reason is each one of these left-hand sides is less than the other. And you can prove that as an exercise as well. So an exercise, and an exercise that I gave you about excluded middle a minute ago. So these are called the structural properties of entailment, and they're properties of an ordering. That is, they're going to hold in any Heyting algebra by virtue of the fact that we assume that this is a product, that it's a Cartesian preorder. If it were merely a monoidal structure, which is requiring less of the meat, it's not a meat anymore, then these things become interesting. Okay, they're not free in any way. In fact, then one can start introducing things like, if you don't want the order to matter, then that's called a symmetric monoidal structure. Okay, where I can swap those things around. There's a symmetry involved. So that's a game you can play. And so what happens is, in answer to the question, is various combinations of these principles, this one, and this one, are deniable. You can decide not to allow them. I claim you don't have anything even remotely sensible unless you have a preorder. You've got to be able, if you're going to have any notion of entailment at all, it has to be reflexive and transitive. Otherwise, I don't know what we're talking about, okay? That would be what I would say. That's why the axioms of a category, the only thing they assume are identities and composition. If you don't have that, it's like, well, it seems to be not very interesting, okay? So you have to have reflexivity and transitivity. But weakening, contraction, and exchange, those are up for grabs. You can do various things with those. And so in answer to your question, depending on which of these I deny, I get versions, other restricted versions of logic. But they have the same general flavor, the same general principle, which is these restrictions are affordances, right? If I don't have weakening, then I can selectively reintroduce it. If I don't have contraction automatically, I can selectively reintroduce it. You get greater expressive power. It becomes a sharper instrument. Okay? So that's why people are interested in these so-called, what are called substructural logics are ones in which you take only a subset of these structural properties. You maybe miss out weakening, okay? Or you miss out contraction, et cetera. There are various things, okay? All right, so that's like a general, like some general remarks. So I wanted to round out the relation to pre-orders, and then Steve will pick this up and go full gas on it with treating in the context of categories. So from our point of view, for these couple of weeks, category theory is another way of talking about type theory, which is another way of talking about logic. Okay, so that's what we're doing. So these things are all of a piece. Okay, so that's the idea. Okay, so now I want to go back to these ideas of equivalence. Oh, sorry. Yeah.
Go back to your use the word decidable very carefully, and I wonder if you can say again how it applies to the P's and NP example. On your reading, would you say that
Well, it's not
decidable or not known to be decidable?
Famously, we know that we have neither proof nor refutation of making it. So that's an example of a proposition that at the moment is not decided. So, in other words, I cannot prove either P equals NP or P is not equal to NP, because I can neither prove it nor can I refute it. I neither know that that non-determinism is useless, nor do I know that there's definitely a case where.
I'm trying to pin down what you mean by decidable. So are you saying that P equals NP is not
Well, the definition is whether the A or not A is true.
So are you saying that, for example, P equals NP is not decidable at the moment?
Yes, at this moment, yes. Because it's not the case that I can prove A or not A is true. Okay, yes?
The dream hypothesis. A proof of the dream hypothesis cannot prove or disprove it, but actually be disproved, because that means there's no counterexample. But actually prove, because that means there's no counterexample. The dream hypothesis cycle.
I haven't quite got that.
The dream hypothesis cycle.
No, that's again an open problem. It's an open problem.
Yes, it's open, but it is known that you can prove it cannot be proven or disproven. Then that means there's no counterexample as proof.
No. I'm not saying you can refute the disjunction of it. That's what I'm saying. The definition of logic, this is the subtle point. It's not the case that it refutes it. It's just it affirms it. Okay? It is positively irrefutable. That I know. That's a theorem. You're going to prove that. Okay? Okay, but that's a different thing. Okay, so that is for sure. Okay? But there are plenty of propositions for which it's not known one way or the other, whether it's true or can be refuted, true or false, and so it's undecidable. Okay, so that's the idea. So that's the I don't know a better way to explain that beyond that. Yes, in the back.
Go to second order, then if you put that for all A, if you go to second order, if you put that for all A quantifier to the inside.
That's what's going on here.
Yeah, if you put it to the inside, then it's not provable, right?
Well, I don't know. I haven't
So double negation of for all A or not A. That thing is not. Am I right?
Did you say wrote the wrong thing down here? Now I have to think about it. Frank, did I
Those
write
should be
this
the
down?
same. I think you can do it with the
Those should be the same because you can get rid of 4 knots.
No, because I think you have the Huygens paradox or something like that, and that will exclude it, but I'm not sure.
I believe that what I have, because I have a proof in mind, and I don't want to give it to you because I haven't believed it exactly. So I believe I have a proof in mind.
Related to the fact that single negation is equivalent to triple negation.
Well, that's true.
But double negation is not equivalent necessarily to
That's right. That's exactly true. Yes. So the statement that is just made is that, there is a separation between A true entails not A true, with brains in. That is certainly the case. you wish. You can prove that quite easily. But this is in general weaker. Okay? And we say that A is stable by definition. If and only if, this is a definition. If and only if not A implies A. Not every proposition is stable. Double negation is stable. In classical logic, when you make these general assumptions, then it is. So in particular, you can say, in the presence of the law of excluded middle, then every proposition is stable. That is certainly true. Okay? So, but it is not the case in general. So this is true. This is a weaker, so as in general situation, this is a strictly weaker statement when you're saying that something, something can't possibly be false is different from knowing that it's true. Yes, that's exactly to say, yeah.
Stable is equivalent to density.
I'm afraid I can't hear you.
Stable is equivalent to density.
Could someone relay? Okay, and leave that as an exercise as well, because I'm getting tired. Okay, so here's another exercise, which is, now it starts to look kind of absurd, but it is the case, that is the case. Okay, that definitely is the case. One, sorry. Yeah, one. The other way is obvious from here, but this direction. This is the case. Okay. The reason so what is that saying? What it's telling us is that negated propositions are stable. Okay, so that's what it is basically saying. Okay, and I'll leave that as an exercise for you as well. These things are not hard, but we're diverging. I'm getting off on a tangent, so I'm hoping to corral us back. Why don't we leave this for the exercise section, okay, to talk about further. Okay? All right. Okay, so let me get back on my intended track. Let's see. What am I going to write with? Okay. All right. So what we're doing, and all of this will make good sense, and it'll come together in time. What we're doing now was talking about various notions of equality. I'll just remind you, and there's a reason why I want to remind you because it's very essential to what comes next. In fact, these issues of equality are completely of the essence when dealing with dependent types. So that's what we'll talk about. So let's remind ourselves. So we had this notion of definitional equality. And we explained, and I was warning you that it's not very conventional, but I was using that notation with appropriate warnings that it's not completely standard notation because nothing is, okay? So let us say, remember this was supposed to be equality of sense or some kind of computational equality. And so an example to keep in mind, I'll just write it in a form that jogs your memory. For any x, sort of x plus 0 is definitionally equal to x, given the definition I gave of plus. You need to know how I define plus in order to know, because that's the nature of definitional equality. And then I made up a word, okay? This is I made it up when I was thinking about these lectures. This is not standard, but I needed a word, which I'll call denotational equality, which is equality of reference. And so I was just writing that as equality, written like that, okay? And the example that we gave there, just to like the kind of thing that should jog your memory, is maybe with x, y, and n, x plus y is equal to y plus x, but not definitionally in n. But not definitionally, okay? They refer to the same mapping. So if you think of this as a mapping from n cross n, arrow n, we have two mappings. We have, if you'll don't mind my loose notation, x plus y is one mapping and y plus x is another. What I mean is send the pair xy to x plus y, etc. Okay, I have two different mappings, so I could write them like this. Okay, there's two different mappings that go there, and they're the same mapping. Okay, well, why are they the same? Well, by virtue of an argument by proof by mathematical induction. I can do a double induction. Here's two numbers. I can go all the possible cases on 0, 0, 0 successor, successor, 0 successor, successor, using the inductive hypothesis and prove, which I won't do here at the board, but you could work it out just for yourself on the basis of the definition I gave, plus, so if I take definitional equality, as I defined it, plus mathematical induction, I'll just write MI, will give you this proof that those are equal. And you can do that as an exercise as well, just so you know how the machine works. It's not difficult at all, it's just to see how to make the machine work. Okay? So they refer to the same map. Yes?
It's an exercise in chapter 1. It's an exercise in chapter 1 of Software Foundations. So
Okay, so good. That's all right, so that too. Okay, so that's like, I find this like handy like heuristic thing to remind me which thing I'm talking about. And then we're going to have a notion of equivalence. And this is going to come up a little bit later, weak equivalence or homotopy equivalence, and this will come up later. But an example of this, it'll be the notation I'm going to use when I motivate this is going to look like that. Okay, which is an example of this would be, and this is going to be, this is supposed to be homotopy equivalence or weak equivalence. And the way we're going to do, what this is supposed to mean, an example of this that we can do is the following idea. The easiest example to motivate, there are others, but the most simple one you can possibly think of is to think of isomorphism of sets, which is bijection of sets. So an example would be that we can take 2, which is 1 plus 1, true or true, the Booleans, defined using type theoretically as 1 plus 1. 2 is isomorphic to 2 in two different ways. Via the identity, I'll just write it over here, and via the not function. Okay? Because there's not is just swapping true and false, and it is its own inverse. Okay? The identity leaves them alone. Okay? So we have two mappings. So we have, here's 2, here's another copy of 2. We have this mapping, and we have this mapping, okay, which crosses them up. So these sets are going to be isomorphic, but there are two different reasons why they're isomorphic. So the way we can write that is we can really say, my notation was too cute, so let's write it like this. Okay. If we had a type of sets, then 2 would be a particular set. It's 1 plus 1. And identity and not are forms of evidence that these are isomorphic types. That's the picture. So this is evidence for some kind of equivalent. I'll write it like that, sorry. And this is for equivalence. The notation is, again, not fixed, but something like that is usually the way it's written. Okay, looking like that. So that's evidence for equivalence. Okay, we'll come back to that a little bit later. But the thing I wanted to get across here, and this is a semi-oblique answer to a question that was asked in this morning's session, which is the idea here that the thing that is going on here is that I have generalized this idea of equality to one of equivalence in which one has evidence for the forms of equivalence. And the thing that is going on here is that this is a particular resting point. Okay, this is a particularly useful point that applies to what we will end up calling discrete sets. So I think I'll wait until I explain that remark fully a little bit later. But the thing you want to see just superficially is that we state this just as a proposition. M is equal to n colon A, just as a judgment as it is with no further evidence. The reason being that the only form of evidence is a trivial token which represents reflexivity, that these are the same map. And here we have some other forms of evidence that is other than identity or reflexivity, like negation, which is a different reason why two things can be considered equal. Here there's at most one thing. So the idea is that we're suppressing the trivial evidence, which is always reflexivity. And this is what is related to, someone asked me about OTT, and it's related to OTT, or the identity. It's related to that. Okay? So I'll come back to this a little bit later, but that is the idea that's going on here. Really, this is an instance of that in which alpha is always reflexivity. But it's customary to just focus on this, because in certain restricted low-dimensional settings, that's the way it will come out. In low-dimensional settings, then this is perfectly adequate for itself. In higher dimensions, you need something more. So what I'm doing is I'm setting up, I'm trying to establish a framework that scales to higher dimensional type theory. That's what I'm doing. So this is a new development of the last couple of years, and I'm trying to do everything in a way that is consistent with those developments. So that's the idea about it. Okay, so why do I make such a big deal about equality? What does that have to do with anything? Well, first of all, it is an interesting question to talk about. Excuse me, Eugene, allergies. It's an interesting question to talk about when two proofs are equal. But what I'm going to do with the theory of dependent types is a situation where whether two proofs are equal or not is of something of prime technical importance, not merely of intellectual importance. Okay, so you can have it at the propositional level. It's just an intellectually interesting question, that whether two proofs are equal and to understand when they should be equal. When we pass to the theory of dependent types, as I'm going to do now, it becomes something that is of technical importance and not just merely intellectual importance. Okay, so here's what we want to do. Okay, so what have I done so far, just so that we know? So what I've done so far, just to remind you yet again, we're focusing on type theory, and initially what we've done is we've set it up as a notation for proofs. But equivalently, what we can do is we can think of type theory as being a catalog of a variety of notions of computation. Okay, so we introduce various forms of type structure. The type structure determines the programming language features. So, for example, whether you have higher order functions amounts to saying, do you have exponential types? Okay? Whether you have structs or tuples amounts to saying, do you have Cartesian product types? Whether you have choices or multiple classes of data corresponds to whether you have sum types, and so forth. So in other words, a programming language is really just a collection of types, right? The type structure determines what the language structure really is. So what people have said is that the idea of type theory is it's a theory of constructions. It's the things you can build, your little tinker toys that you can build with to do your math, or equivalently, your programming. So type theory is a theory of constructions. From that point of view, logic is an application of type theory, because there are particular constructions which correspond to proofs. But there are other constructions, like of the natural numbers themselves, or of geometric objects, that don't correspond to proofs of particular propositions. They're just mathematical constructions. So what we're doing is we're interested in the general concept of what is a mathematical construction. Okay, and that's where the terminology calculus of constructions comes from, by the way. Okay, this is the origin. And in fact, that's why intuitionistic logic is sometimes called constructive logic, or the doctrine is sometimes called constructivism, because Brouwer emphasized the idea of a construction in the sense I'm describing. And in fact, Brouwer's dictum is the idea, the principle that mathematics, rather than mathematics being sort of a further development of logic, that is, mathematics builds on logic, that it's the other way around, that logic is just a particular corner of mathematics. And I would say, from a modern perspective, actually it's just a particular corner of computer science. because math itself is just a corner of computer science. Okay? No, that's the idea. Because computer science is based on the idea of constructions in computing. And Brouwer's point was you can build all of mathematics on the idea of construction, which is the idea of computer program. So really, it's all computer science. Okay? Computer science is the queen of sciences, if you ask me. Okay? It used to be people thought it was math, but it's not. Okay? It's actually computer science. So that's the thrust of what we're trying to do here in talking about intuitionistic logic. And this is the reason why I have the point of view that the structure of programming languages is not up for grabs. Okay? It's a matter of scientific discovery. It's not like, oh, whatever, you know, some guy or gal somewhere who's very charismatic comes up with some crazy ass thing and therefore it's good. Okay? That's like not what we're about. Okay? So it's like a different perspective on what programming languages are about. Okay, so what we've done so far is we've set up, well, propositional logic. So these are kind of elementary constructions, various kinds of constructions. So these types. So what we have is the empty type 0. We have 1. We have A cross B, A plus B, A arrow B, okay, which in logical terms are false, true, conjunction, disjunction, and implication. Okay? So this is what we have so far, and all the terms associated with it. So that's a good bit of stuff. But now there's going to be some other stuff. And the thing that I want to talk about here is the notion of family of types. Okay, this is critical. And what this is you can think of it as a formulation of or a generalization of, well, so you can think of it as a generalization, really, of the concept of a predicate or a relation as it comes up. Okay? So, for example, if we look at the elementary property of a number x being even, okay? And in fact, to be emphatic about it, that's right. Let's assume we have the natural numbers around. I haven't gotten yet to talking about how we do that, okay? But we can say there's a proposition, even of x. The proposition is even. The idea is I want to think of this as a propositional function. So this can be thought of as a predicate. That's the usual way to think about it. But because we're in a constructive setting, it's not a predicate. So this is like another pernicious, annoying thing that people do, okay? Which is because they equate the idea of a proposition with the idea of a Boolean, they therefore equate the idea of a predicate with a function that returns either true or false. This is as wrong can be. It's just wrong. So things like assert statements in C or something like this, it's an abusive use of the terminology. Because what they are is there's a difference between a function that returns a Boolean and a proper predicate. I'll come back to that later. So this can be thought of as a predicate. Right, that's the usual thing. But it can also be thought of as a propositional function. All right, propositional function. Because you can think of this as describing a mapping. Just make that be a big long arrow. For every x in n, even of x is a proposition. It's something that yields a proposition when applied to a number. So it's a propositional function. So I write it like that so you can see that clearly. Or another way to say it is it's a family of types. In this case, indexed by n. And that's the interesting one, because we can think of it, another notation for that, I'm not really going to use this, but you can look at it like this. Even of x is a prop. It can be thought of as a family for every x in n. That's some sort of, familiar-ish looking notation for the same thing for what I've written over here. Okay? Now, why is this an important or interesting idea? Why is this perspective interesting? Well, it's because of the props as types principle. Remember, the idea of something being true is identified with having an inhabitant. Truth means I have a proof. A proof is an object, so having a proof, an element of this type. So I can say, I can make statements about when certain numbers are even, okay? And I can maybe generically in X under some additional conditions about X. And the idea will be, okay, so the idea is that when I do that, what I am doing is I'm exhibiting a family of types in that if you give me any particular choice of number, it's going to give me back a proposition which has inhabitants or not. So for example, even of 3 will be uninhabited. That's what we're going to say. You won't be able to find a term of that type, assuming I gave a definition of even. I didn't actually do this so far. I'm roughing out the general plan. Even of 2 will be inhabited. That will be an example. And in general, we're going to have an infinity of propositions going across here, expressing the evenness of each of the natural numbers all the way across. So these are all indexed by the natural numbers. So this is over 0 goes to here, 1 goes to here, 2 goes to here, and so forth. Okay? There's another way to think about this, another way to think about this diagram, okay, is to think of it as a big kind of fat sum over here. And what we do is we isolate what are called the fibers over each number. So the idea is that what we do is we look here, and what this is you can think of this as the big, I'm going to use a notation which I'll define later, the big sum of even. The idea is that in this picture that I'm drawing, what I will have at any spot is a number, okay, together with a proof, let's call it P, that number is even. And if that number isn't even, there won't be such a pair in it. So if I pick any number here, okay, like let's say 2 down here, I can look at all of the slice, this little slice, this is called the fiber, okay. I can look at the fiber over 2 consists of all of the pairs of the form 2 comma something, okay, are written like that. And that fiber corresponds to the instance of this family corresponding to x being equal to 2. And if I want to look at the instance of the family corresponding to x being 3, it'll be that fiber, and there'll be another fiber all the way over for each of the numbers, whichever ones we want. In some cases, the picture is a little misleading because the fiber will be empty. There will be none. Okay? There's no reason why it has to have any particular size. But the intuition is that you look at this big so-called total space, okay, and then you look at the things that project down, in this case by the first projection, that project down onto a particular number, and all the ones that project down are to be thought of as sitting on top of each other. They're in the same vertical dimension. So there's one here, and one here, and one here, and one here, and one here. Maybe there are none, okay, but whoever they are. These are all the things of the form 4 comma p, and they all sit above 4. So that's called the fiber over 4. So that's another way to think about what a family of types looks like. So it's a propositional function, it's a family of types, or as this terminology goes, it's a fibration. Okay? That's another way to think about it. So people will describe, even in this kind of context, they'll describe it as a fibration. When they describe it as a fibration, this is what they have in mind. Okay? This is the kind of picture that they have in mind. Okay? All right, that's going on. So these are just different ways of thinking about the same concept. Now, the reason that equality is so important in this setting is because of the principle of what should be called, which is called functionality or functoriality, or respect for equality. So functionality equals respect for equality in various senses. This is the central notion, and the idea is this, is that if in some A I have B, which has, let's put a little x there to indicate it varies with x, is a type. It's written like that. And if you give me, there are various things we're going to write down. So first thing we'll write down is this. And if you give me M, which is of type A, then you can form an instance, M for x, b, b sub x will go in here, is going to be a type. So that's the first thing. So the idea is if you have a predicate over a domain, all right, that's one way to think about this, because you have a family of types indexed by a type, so it's a predicate over a domain. If I have an instance of its domain, then that predicate can be specialized to that particular instance. But the functionality condition says more. It says if you have such a thing, and you give me equal, and now here's the issue, certainly definitionally equal things, that's a starting point, then I will know that the instances are definitionally equal. So that's the first principle. So we get the notion of definitional equality of types. So in the case of evenness, you see, now that we have the idea that an ordinary, that is a variable ranging over a type, can occur within a type, well, this is a prop or a type, that I use them interchangeably at the moment, then the idea is that you have this variable that can occur in here. So if I give you definitionally equal instances, then they are going to be definitionally equal types. And the importance of being definitionally equal types is that typing respects definitional equality. Okay, so I assume you've written this down. So let me write down a few things now that we're starting to establish some fairly large machine now. So let me try to be careful about writing everything down properly. So we're going to have the idea of gamma being a context. We're going to have the idea of definitionally equivalent contexts. We're going to have the idea of a family of types indexed by gamma. And we're going to have the idea of definitionally equivalent types, families of types. And we're going to have the idea of an element of the type and the idea of definitionally equivalent elements of that type. This is the most basic setup that we need. Okay? So this is the framework. The most important thing here at the moment is definitionally equal types classify the same elements. So let's write B here, A, if A is equivalent to B. This is important. Okay? So definitionally equivalent types classify the same terms. So if you can show that two types are definitionally equivalent, then if you have a term of the one type, then you also have a term of the exact same thing is a term of the other type, of B. Okay, so that's a central principle. Now, I haven't told you what exactly are the principles of definitional equality of types, other than by a substitution. So there are substitution principles going on. So and I use them here. Okay, so I used it here. When I substitute for x, I get a type out of the particular instance. So in general, right, we're going to have substitution rules that look like this. With x is in A, if I know that B is a type, then I know if M is in A, it's related to this thing, then I know that M for x, B, is a type. Those are instances. Okay?
I have a quick question because I don't really understand. Type is this a particular type?
No, it's just a judgment saying this is a type. Like early on I said something is a prop. I'm now doing everything in type speak. Okay, I can do it in prop speak if I want, but I've decided to settle on constructions as a central notion. And so I'm doing everything using type terminology.
Okay. So we have basically two different kinds of judgments. We can say that.
Yeah, there are three kinds of judgments. Something is a context, which I haven't fully explained yet. What is A is a type and M is a type A. Okay. Plus their associated definitional equivalences. Okay. So these are important. But I was trying to motivate them by like of this predicate. And then the other rule, I won't write it again, is this rule. So this rule, so that rule is this rule. and then this rule as well. So if you wanted to really write it out fully, it says if you have a family of types B indexed by A, and if M and N are definitionally equal index elements, then the types you get back are definitionally equal. That should be B. And therefore, by this rule, they're interchangeable as classifiers. So somehow everything is driven by that particular rule. Okay? So that starts to be the beginning. This is the beginnings of it all, okay, of the idea of dependent types. Now, I sort of acted like even was a primitive notion. In fact, it'll be definable, but it needs a little machinery of inductive definitions that I don't have yet. So I'm going to be a little loose about exactly which are the things, except in one case, which is coming up next. Okay, we'll do that. I'll talk about the identity type. Okay, so let me check for a minute what's going on here. I want to make sure I say the right thing here. Right, okay. I have to figure out the right moment to bring this in. Okay, so this is the general theory, and so my first point is, as soon as you have the idea of family of types, so this is expressing the idea of a family of types, because gamma is, what is gamma? Gamma is a bunch of declarations of variables. So gamma generally has the form x1, a1 through xn, an. So that's the notation. I mentioned that before up here. Okay, so that's the idea. So what this says is that this is a family of types indexed by the variables in gamma. So we have, as I mentioned, if x, so let's do another one. Let's say if x, y are in n, those are two variables, then maybe x less than or equal to, and I'll just write the n on there just to be, or I'll put it over here. It doesn't matter where I write it. Let's put it here. Okay, is going to be a type. So that is an example of a relation. A relation is a two-argument propositional function, or a family of types indexed by two variables, right? For every choice of x and every choice of y ranging over n, I get back a type. The type of proofs that x is less than or equal to y for that particular choice of x and y. Okay? That's what's important. So the thing that I'm trying to inculcate in you is to stamp out your Boolean prejudices, okay? Predicates don't stand for like a Boolean. That's like, you have to undo that thought, okay? A predicate is a family of types. And what you do is when you instantiate it, what you get back is a classifier, which is the classification of all the proofs of that instance of the family, okay? So from this being a predicate, I will know, therefore, that 3 less than or equal to 7 is a type. It's the type of proofs that this number is less than that number. Okay? This is the way you must think constructively. There's no other way. Okay? You must think in those terms. As soon as you start getting used to that, then a lot of things will make more sense to you. And in fact, the power of this thinking is to be quite honest, breathtaking. In the course of my career, I've had some of the most astonishing experiences that are kind of hinge on this kind of constructive perspective. So I think that is the thing to get across. Okay, so you're with me so far on that? Okay, so 3 less than 7 is not a Boolean. It's a type. All right. So, yeah. Oh, absolutely, yeah. So there's another type. Let me just erase because I don't have enough room. That's also a type. It will not be inhabited. Okay? You won't know a proof of that type. Therefore, thought of as a proposition, you will not be able to say that it's true. Okay? So that's the idea. Yeah, so it's the inhabitation of the type. I mean, that's the thing that matters, because this goes back to my basic principle of true means I know a proof. Equivalently, that the type associated to the assertion is an inhabited type. Ah, okay, so there's another way to think about it is there's a conceptual economy. All sorts of seemingly disparate things collapse down to one thing. Okay? And that's good, right? That's always good. All right, other questions? Okay, what time am I supposed to go to? Now? Yes, this is pretty much my slot? Okay. Then I want to leave us at a decent resting point. This is not bad, okay? The other thing, as a resting point, the other thing I want to say, though, about it is this, okay? So that's the first general setup. Now becomes the next question, which is to revisit this notion of equality, and in particular the idea of equality of reference. Because what do I want to say, what I want to get to is, and this is the kind of example I'm going to give you is a very famous one, okay, that has come up many times because every naive language designer comes up with this idea and then like falls flat in his face, okay? But here's the idea. You can think of this as some people, there are various ways to write it. We can say, whoops, let me leave myself some room. The idea is that we can look at the type maybe 0 dot dot x is going to be a type. And that's supposed to be thought of as, the idea is it's supposed to be, 0, 1 to up to, let us say, x minus 1, something like that. Okay, or x, I don't care really, whatever you want to do. Okay. I'm just picking one of many examples out. Okay. So people have tried to do this. Okay. These are sometimes called sub-range types or various things like this. So the critical idea is that, or you can think of it as a predicate. You can think of this as expressing the predicate that you're expressing a predicate. You can think of this as a predicate in y that says, well, given y in n, it's the idea that y lies between 0 and x, let's say, if I did it like that, in n. That's equivalently what it's expressing, okay? And this is for some fixed x, okay? Right? That's a way of thinking about it. So that's supposed to be a type. Okay, so here is the kind of thing that people run afoul of. And the question is, suppose I have now x and y in n, and I want to say something about the relationship between the type 0 to x plus y versus, I'll just write versus, the type 0 to y plus x. And what is the relationship between them? Okay, because this is a type on this basis, assuming I had plus around and stuff like that, like I usually do. And this is a type. Really, writing 0 dotted is just like a nicety. I could have called this up to of x if you want, okay? But anyway, a lot of times people will write it in this notation, right? It's just a way of presenting it, okay? The question is, are these the same type or are these different type, or what's the relationship between them? This ends up being incredibly annoying, okay? It becomes really a major problem. The reason is that we talked about before, x plus y is not definitionally equal to y plus x in the setup that I gave you. It's not a definitional equality. It's in fact a propositional equality. That is, this has to be proved by induction. So this is not true. This is true, but it requires an induction. It needs evidence. And the evidence is going to influence what is the relationship between these two types. And so that is a critical question, distinguishing what are called intentional versus extensional type theory, which I'm going to explain. I guess I will explain next time. So this will serve as a tantalizer for you, since I'm at the end. So the issue I want to get at is, once you have families of types, then you have the idea that terms make their way into types via the substitution principle, and that those families should be functional, that is, they should respect definitional equality, certainly. The question is, should they respect other forms of equality, like a referential, a denotational equivalence? These are the same mapping, so maybe these two types should be equal, right? Why not? Maybe they should be equal as types. And if they were equal as types, that would be pretty damn convenient, because anytime you had an element of this type, then you'd have an element of this type as well, and it would be all like nice and easy and very simple. But it's a little stickier than all that, and I'll explain that next time, so that'll be tomorrow. I'll start talking about this. So right now I'll leave it as a puzzle for you to think about. okay, is how to handle this kind of a situation and how it's going to happen. What we're going to do is we're going to generalize the idea of functionality to the idea of functoriality. And that will give us some idea of what we're going to do here. So, all right, so that's what I want to say right now. So let's stop there.